So what I want to do is show you a little bit of vectors and the notation and things like that, and then do some of those word problems that are on that worksheet. So I'll do like one or two examples from each one to show you how they work, and then if you have any questions, let me know. But first of all, a vector is any quantity with a magnitude and a direction. So there are many different models for vectors. Vectors can be distance, vectors could be force, things like that. So anything with a magnitude or a size and a direction. Okay. So here's one of the ways we can represent vectors. If I draw an x, y coordinate space, I can draw a vector anywhere on here, and the location of a vector does not matter. What really matters is where it starts and where it ends. So once I draw a vector, I can actually pick it up and move it anywhere I want. So if I draw a vector at the origin, and I show an arrow to represent what direction the vector is going, and I can put an arrow at the end to represent the terminal. Now, for this one, it does look like a ray, but this is a vector. One of the differences is vectors do end. That arrow represents its direction, but it actually does end at that arrow. So this is what's called the terminal point. And then this point down here would be called the initial point. Now, one of the ways I can represent a vector is I can use what's called XY notation. So this is called coordinate notation. Coordinate notation is very useful when I want to add vectors that are not right to each other. So we'll be doing more of those on those worksheets. So when we write a vector in coordinate notation, you draw a bracket, you've got the x coordinate, the y coordinate, and that's your vector. Now, those are not a point, so we need to make sure we have a bracket. And this x represents the distance in x from the initial point to the terminal point, and this represents the distance in y. Okay. And if I move the vector, I don't do the distance from the origin, it's always from the initial point to the terminal point. So that's one way. This is useful for, again, adding. The other way I can represent is to use what's called magnitude and direction. And with this, you'll get a magnitude, which is just the size, so it's the length of the vector. And you'll also get an angle. So for this one, and I might say that it's 3 feet, and it's at a 40-degree angle or something like that, and that would be magnitude direction. One of the things that we need to be able to do is change between these, and I want to show you how to do it. Now, I'm going to end up doing it long way, and then there's some tricks that you can remember that really help you with the worksheet. So let's do the one way. So for this first example, they give you the direction and the magnitude, and we need to find the x and the y. So what I'm going to do is I'm going to find x first. So this would be the adjacent, and I know the hypotenuse. And you can see that cosine will find me that x coordinate. So I can do the cosine of the angle equals the adjacent over the hypotenuse, 65. So x is going to be, multiply the 65 to the other side, 65 times the cosine of 50. And notice, really, the 50 degrees didn't matter, the 65 did not matter for any triangle that is done this way. X is always going to be the magnitude of that vector, or the length of it, times the cosine of the angle. So this is one of the first things that's nice to remember. Now, if I ignore that and I say, okay, well, let's go ahead and find y. Well, the only difference is y is the opposite, and I still know the hypotenuse. So it's still going to be 65, and it's still going to be 50 degrees, but instead of using cosine, I'm going to use sine. So this would be the sine of the angle is equal to x over 65. Oh, not x, y. So y over 65. Multiply the 65 to the other side, and y equals 65 times the sine of the angle. And for this one, again, the angle and the magnitude did not matter. I could replace those with any. And y is always going to be 65 times the sine of the angle. So if you ever have magnitude and direction, you can change them to x, y if you need them. Now, before I talk about the next one, the book, sometimes we use this direction notation, north, south, east, west. I just want to show you one of these so you can see what the book's talking about. If you take a look at this first vector A, we're mainly going east, but we're going 25 degrees south of that east. So you'll see them call this 25 degrees south of east. And for the other one, we're mainly heading north, but then we're going 35 degrees east of that, so this one will be 35 degrees east of north. So we'll be using that notation sometimes, so they just want you to get used to it. Okay, so now here's the other direction. How about if I give you x and y, and you need to find the magnitude and the direction? So if you look at this triangle, they give you the x and the y, and you notice that the length of it is just going to be the Pythagorean theorem. It's the hypotenuse of a right triangle. Okay. So for this one, the magnitude is just equal to the square root of, and I'm going to write them as positive since I'm just going to be squaring them. So the square root of 40 squared plus 25 squared. You put that in your calculator. That'll be the magnitude. Now, in terms of the angle, I need to find an angle, and I know parts of the triangle. So this would be the opposite. This would be the adjacent. So for this one, we're talking about tangent. So I can write a little trig thing that says the tangent of x is the opposite over the adjacent. And so x is just the inverse tangent of y over x, and because they're both negative, I can even write it as 25 over 40. Okay. And so I can get the magnitude and direction. And for both of those, again, the triangle was not unique. That'll work for any triangle. So here's two more things to remember in order to change it back to direction: magnitude. The magnitude is always equal to the square root of x squared plus y squared, which is the Pythagorean theorem. And the angle is always equal to the inverse tangent of the y value over the x value. Okay. So those two things can really help you when you're changing them back and forth, so you don't have to draw the triangle each time and solve for parts of the triangle. So these combined with the other ones are going to be a lot of the things I'm going to use in that second worksheet. Okay. So to add vectors, all you do is you add the x to the x and the y to the y. That's why the xy notation is so very useful. So here's a rule that shows you that. You add the x's together, you add the y's together. Don't worry about the notation. If you take a look, that's all you're doing. So if you see the example they want me to add the two vectors together. What I can do is take each vector and change it into the vector notation. So this one right here would be to the left one and up 2. And this one right here is going to be to the right 4 and up 3. So if I add those two together, I add the x's together, I add the y's together, and this is what's called my resultant vector. Now, one thing that's kind of cool to notice is that if I pick up one of these vectors and I put it at the end of the first vector, and it doesn't matter which way you do it. So I'm going to pick up the c vector, and I'm going to move it to the end of the a vector. So it would look like this. And remember, vectors, the location of a vector does not matter. It can be moved anywhere in the coordinate space, and it's still the same vector. So if I take a look at the resultant vector, it would be from where I start the first one and where I end the last one. So notice my resulting vector is over 1, 2, 3, and up 5. So the combination of those two vectors is just like, I think of them as stringing them together. You take where the one ends and start the next one, and if you have multiple ones, you just keep on going. And the order doesn't matter. If I pick up A and move them to the top of C, it ends up being the same vector. So, and when you add these, sometimes it's useful to do that, and sometimes it's useful just to write down their coordinates and add them together. It's the same thing. Okay, I want to get to some of the problems that you had to do. So this worksheet gets progressively harder as you